So we're going to start from Hess's law. What is Hess's law? I'm going to explain that. Statement of Hess's law explains us that if a chemical change takes place by several different routes, the overall energy change remains same regardless of the route by which the chemical reaction or the change occurs. So we can say that the initial and the final conditions are same. For the explanation, if you take the example of A, B, C, D or a general reaction, we can say that let A be converted to the D from a path where the enthalpy change is delta H, and the other routes by which that process can occur are A to B, B to C, and C to D. So the other routes will have the enthalpy change delta H1, delta H2, delta H3, and according to the Hess's law or the Hess law, delta H is equal to the sum of all the other paths through which all the other energy of the paths through which the chemical reaction has occurred. This is an example of a conservation of energy, and Hess law is the application of more fundamental law of conservation of energy. So sigma delta H is equal to 0. That means if one goes from A to D directly and comes back to the A through B, C and other paths, then delta H will be equal to 0. That means that if we let A that can be converted into D directly in a single step and the heat evolved will be delta H, then the other steps will have delta H1, delta H2, delta H3, whose sum will be equal to delta H. So we can say mathematically that sigma delta H cycle is equal to 0, and it is known as the Hess law. The applications of Hess law include that it is used in indirect measurement of heat of combustion, heat of formation, heat of neutralization, and lattice energy of ionic compounds. So the explanation of this law can be that there are many compounds in which delta H cannot be made directly by calorimetric methods, as we discussed before. The calorimetry and the calorimeter and the method that was used to measure the enthalpy change. This is a very important topic of enthalpy, a very basic topic of enthalpy that is really very significant related to the studies. So the reason is that some compounds like tetrachloromethane CCl4 cannot be prepared directly by combining carbon and chlorine. So similarly, it does not compose and decompose also easily into its constituent elements. So and the next example is that boron oxide B2O3 and aluminium oxide Al2O3 provide problems for the measurement of standard enthalpies of their formation. So we cannot get to the formation enthalpies of these compounds and their reactions. So in these cases, it is very difficult to burn these elements completely in oxygen because a protective layer of oxides cover the surface of the unreacted elements. So we can say that the Hess law is really very important, and similarly heat of formation of CO cannot be made directly due to formation of CO2 with it. So we need Hess law to measure the enthalpy change of many different reactions. An indirect determination of an enthalpy change uses an enthalpy cycle, which is based basically on Hess law. This method is used when the reaction is very difficult to carry and related reactions can be measured more easily through Hess law. So here's an example of formation of Na2CO3. I'm going to quote here. In the single step process, the reaction will be 2NaOH plus CO2 in gaseous form and NaOH in aqueous form, which is converted into Na2CO3 aqueous form plus H2O in liquid form, and the delta H is minus 89.08 kilojoule. So the next thing I'll explain it in two-step process. The two-step process includes NaOH plus CO2 that is converted into NaHCO3 in aqueous form, and the delta H1 is minus 48.06 kilojoule. So we can easily understand that delta H is equal to delta H1 plus delta H2. One-step process is equal to the two-step process sum. So we can calculate the enthalpy change through, or we can prove the enthalpy, and we can calculate the delta H, delta H1 and delta H2.